everyone, I am Bhageshri Guruna. Today I am going to present my project named Web-Based Visualizer for Structural Representation of C Program. So coming to the introduction part, whenever we write a C program, we see it as a normal text containing of keywords, variables, operators and statements. However, computers do not understand programs in the same way as humans do. Before executing any program, a compiler converts the source code into different internal structures. So these structures help the machine understand the logic, flow, and behavior of the program. The main aim of this project is to visually represent these internal structures so that students can easily understand how a compiler analyzes the program behind the scenes. So the structural mapping of code is the process begins with the structural mapping. The compiler first converts the program into meaningful units called tokens. Then it builds hierarchical structures that represent the syntax and logic of the program. So it also analyzes how the program executes, how decisions are made, how data moves between variables. This concept is especially important in modern software development, artificial intelligence, and cybersecurity because security tools depend on these structures to detect vulnerabilities. So the next is tokens and syntax trees. So the first stage is lexical analysis. Here the source code is divided into small units called tokens. Examples include keywords like int and if, identifiers like variable name, operators like plus, minus, and less than. So this process is based on finite automata and regular expressions. The second stage is the abstract syntax tree or AST. An AST represents the logical structure of the program in a tree format. It removes unnecessary symbols such as commas, semicolons, and brackets and focuses only on the logical relationships between statements. This makes the program easier to analyze and understand. So the slide 4, content flow and data flow. After creating the syntax tree, the system generates two important graphs. The first one is the control flow graph or CFG, where it shows the path that execution follows through the program. For example, when an if statement or a loop appears, CFG shows all possible execution paths, and the second one is data flow graph or the DFG. So it tracks how data moves through the program. It shows where variables are created, modified, and used. This helps the developers understand dependencies between different parts of the code. The next is code property graph. The most advanced structure in this project is the code property graph or CPG. It combines the abstract syntax tree, control flow graph, data flow graph into one unified graph. So this unified representation provides a complete picture of the program where it is widely used in security auditing, vulnerability detection, automated bug finding, artificial intelligence systems for code understanding. Because all the information is available in one graph, analysis becomes faster and more efficient. So the project working process is, it contains major three phases where the phase 1 is reactive interface. Here the user writes the code in a web editor. As soon as the code changes, the system automatically starts analysis. And the second phase is computation pipeline. So the three operations are performed: lexical scanning to generate tokens, and the syntax parsing to build the AST, graph generation to create CFG, DFG, and CPG. And the third phase is interactive rendering. The generated structures are displayed using cytoscape.js. Users can zoom graphs, drag nodes, and explore connections interactively. This creates a professional and user-friendly visualization experience. So now next, coming to the output part, the system generates several outputs. First, it displays the token table showing each lexeme and its classification. Then it displays AST for program structure, CFG for execution flow, DFG for data movement. Finally, it generates the unified code property graph that combines all representations into one powerful model. Next, coming to the connection to automata theory, this project directly relates to concepts studied in the automata theory and computation. So, the lexical analysis uses finite state automata, syntax analysis uses push-down automata and context-free grammar, and the flow analysis uses graph theory, and the complete program analysis resembles Turing machine computation. So, this project demonstrates how theoretical concepts are applied in real-world compiler and the security system. So, now coming to the coding part. So, this is the code for our website. So, the output is, so here is the code where the user can paste any C code, and while after pressing the button compile and analyze, the uh, output is generated as the first phase goes lexical token, where the program is broken into small units called as token, and the AST syntax, where it is abstract syntax tree. It generates a tree-like structure using the source code provided by the user. The next is control flow graph. So the CFG tree is as follows. The next is DFG, and the last one is PPG, unified PPG. So you can paste many other codes. It is editable. So for example, now I am taking this program. So if we paste that program here and click on compile and analyze, so the tokens are generated as follows. You can also take another two programs. So the output will be generated for each and every program pasted by the user. So here is the output. So now coming to the conclusion part. To conclude, this project shows that automata theory is not just a classroom subject. The concepts of automata, grammars, and computation are actually used in modern compilers, AI-based coding assistants, and cybersecurity tools. By converting source code into visual structures, this project helps bridge the gap between human readable code and machine understandable logic. So thank you.